Welcome everyone. During this lecture we're going to introduce momentum, we'll provide a definition of a collision, we'll define impulse, and then we'll explore an impulse momentum application. Let's begin by defining momentum. Momentum is just a measure of an object's relative influence during a collision. With another object. The symbol for momentum is P, and momentum is a vector quantity, so we'll indicate it by including an arrow over the P. So how do we measure the amount of influence that an object has during a collision with another object? Well, the more massive the object is, the more influence it'll have during a collision. So mass is an important consideration. And the other consideration is how rapidly the object is traveling. In other words, its velocity. The greater the velocity, the more influence the object will have. So we'll also include velocity. This is the momentum equation. And from this equation we can extract the units. Of course, mass is described in kilograms, and velocity is described in meters per second, and therefore the units for momentum are kilogram meters per second. Let's consider momentum conceptually through the following example. In this example, a ping pong ball and a bowling ball are traveling with equal velocities. Which object has the greater momentum? Well, if we evaluate the momentum equation, each of the objects has the same velocity, but of course a bowling ball has much greater mass than a ping pong ball, therefore the bowling ball will have the greater momentum. And so the answer is the bowling ball. Now here's another question. Could a ping pong ball have greater momentum than a bowling ball? And the answer to that is absolutely. If the bowling ball is traveling with a low velocity and the ping pong ball is traveling with a very high velocity, then the product of mass times velocity for the ping pong ball could potentially exceed the product of mass times velocity for the bowling ball. So the answer is yes. A ping pong ball could have a greater momentum than a bowling ball. Let's now introduce the definition of a collision. First, let's notice that the word collision is contained within the definition of momentum. In other words, momentum is a measure of an object's relative influence during a collision. And so what is a collision? Well, a collision is any event in which two or more objects there are two types of collisions. The first is when the objects converge. In other words, the objects come together. Or the second type of collision is an event where two or more objects diverge or separate. For example, a car accident is an example of a collision that involves convergence. There can also be divergence if the cars separate after the accident. Another example, tackling an opponent on a football field. And of course, that's another example of a convergent collision. Here's another example. Throwing a ball is actually considered to be a collision. This is an example where two objects separate. The arm and the ball separate as a result of the arm throwing the ball, and therefore this is an example of divergence. Another example of a collision is catching a ball. And of course, that's a convergent event. An explosion is considered to be a collision. And of course, an explosion is a divergent event because the objects that were once contained now separate into many pieces. Shooting a bullet from a gun is also considered to be a collision. And of course, that's a divergent event. There are many other examples. I'll introduce one more. That doesn't sound like a collision, but it actually is. Expelling water from a faucet is considered to be an ongoing collision. And since the water is separating from the faucet, of course, this is a divergent event. So as you can see, we have a much broader definition of a collision with respect to what we ordinarily consider to be a collision. We will now define impulse. Impulse is a measure of the ability to change an object's momentum. Now, in order to change an object's momentum, a force must be applied over a period of time. So it's important to note that impulse is related to force and time. But what is that relationship? Well, in order to show that relationship, let's begin by evaluating the momentum equation. Earlier, we developed this equation. We stated that momentum equals mass times velocity. Now, impulse is related to the change in an object's momentum. To indicate change, we're going to install a triangle or a delta. Delta, of course, means change. So a change in momentum will equal mass times the change in velocity. Now I'm going to introduce a trick. The trick involves dividing both sides by delta t. And let's see what that produces. So we would have the change in momentum over the change in time will equal mass times the change in velocity over the change in time. Now this should look familiar to us. We've seen something defined as the change in velocity with respect to time. Do you recall what that is? Well, of course, the change in velocity with respect to time is just acceleration. And so, the change in momentum with respect to time is just equal to mass times acceleration. Now this should look familiar as well. Earlier, we discussed the fact that mass times acceleration is directly related to force. And so, the change in momentum with respect to time just equals force. And if we solve this equation for the change in momentum, of course we would multiply both sides by delta t, the result would equal force times the change in time. And so here it is. In order to change momentum, we need to apply a force for a period of time. Now, force is a vector quantity, so we'll note that with an arrow on top of the force. And force times change in time is just defined as impulse. So this product is called impulse. Now, we use the word impulse because generally we assume that the time of contact during a collision is small. So when two objects interact through a collision, the collision takes place over a very short amount of time, and therefore we decided to name this product impulse. For the same reason that you would describe somebody who shops very quickly without thinking about their purchase, you would describe that person as impulsive, right? Not spending a lot of time on making that purchase decision. For the same reason, we decided to call the product of force times time impulse. Even when the time of the collision is very high, this equation still applies. So impulse doesn't necessarily restrict the amount of time involved in a collision. However, the word impulse takes into consideration the fact that most collisions occur over a short period of time. And so, impulse is abbreviated now by the letter I. It is a vector quantity because it has a direction, and I just equals force times change in time. It also equals the change in momentum, right? It also equals delta P. And the change in momentum, just like the change in any other physics parameter, just involves taking the final momentum in this case and subtracting the initial momentum. Which could be further expanded as, if you recall, momentum is just defined as mass times velocity. So we can expand this as mv final minus mv initial. Now this is a very, very extended relationship. What I'd like to do is reduce it down to two usable forms. And so the first form for impulse is specified right here. Force times change in time. The second form for impulse is shown on the end of this relationship. In other words, impulse also equals mass times final velocity minus mass times initial velocity. So we'll note that relationship as well. And we will decide which form to use based on what is provided to us within problems that we're assigned to evaluate. Let's now discuss the units for impulse. As it turns out, there are two units that may be interchanged for impulse. The first units come from the first equation. In other words, impulse equals force times time. The units for force are newtons and the units for time are seconds. So the first unit is the newton times the second. We call it a newton second. Or the other unit that's available is provided by this side of the equation. In other words, impulse equals mass times velocity, and mass, of course, is specified in units of kilograms and velocity specified as meters per second. And so that is the alternate unit, a kilogram meter per second. And by the way, it's important to note that this is the same unit that we use to describe momentum, because impulse and momentum are directly related to one another. So we have the freedom of either using the Newton second to describe impulse, or we can use a kilogram meter per second to describe impulse. We will now introduce an application of the various topics that we have discussed. In this application, a 145-gram baseball initially traveling at 40 meters per second is struck by a bat as shown below. Immediately afterward, the bat travels in the opposite direction with a speed of 60 meters per second. If the time of contact between the bat and the ball is 1.5 milliseconds, let's begin by determining the ball's initial momentum. Now, of course, the symbol for momentum is P with an arrow on top. So we need to find the ball's initial momentum. Now, we developed the equation for momentum. The initial momentum is simply given by the mass times the ball's initial velocity. And notice that I'm placing arrows on top of the momentum as well as on the velocity to note that the direction is important because these are vector quantities. In other words, if the ball is traveling to the right, I'll enter the velocity as a positive value. If the ball is traveling to the left, of course, we'll enter it as a negative value. Okay, so in this problem, the ball's mass was given as 0.145 kilograms, right? Let's take a look. The mass is specified as 145 grams. Of course, we need the SI unit for mass, and we will therefore bounce the decimal point over 3 times, 1, 2, 3 to the left, right? Because there are 1,000 grams in a kilogram. Okay, so the mass equals 0.145 kilograms, and we'll multiply that by the initial velocity. The initial velocity is 40 meters per second, but the ball's traveling to the left. Therefore, it has to be entered in as a negative quantity. So the velocity initially is negative 40, and if we multiply those two values together, we obtain negative 5.8, and of course the units for momentum are kilogram meters per second, right? The mass is in kilograms, the velocity of course is in meters per second, so our units are kilogram times meters per second. In part B of the problem, we would like to determine the impulse delivered by the bat to the ball. Of course, the symbol for impulse is just I with an arrow on top. And we have two equations to consider in order to find impulse. Let's take a look at those two equations. Here they are, and I'm going to take this opportunity to put these equations in a box. They are very, very important. And so, should we find the impulse through force times time, or should we find it through mass times final velocity minus the mass times the initial velocity? Well, we don't have the force available to us at this point, and so the second form is more usable to us. Let's use it. And so the impulse can be derived through the mass times the final velocity minus the mass times the initial velocity. In this case, the mass, again, is 0.145 kilograms. The final velocity, let's take a look at that. The final velocity equals 60 meters per second, and of course the ball is traveling towards the right, and so the 60 will be entered in as a positive value. Minus, the mass again is 0.145, and the initial velocity, again, let's note that the ball is traveling towards the left initially at 40 meters per second, so we're going to enter it as a negative 40 into our equation. Which produces a double negative, of course, and the effect of a double negative is just a positive. So if we enter these values into our calculator, the impulse equals positive 14.5 kilogram meters per second. Of course, we have the option of using Newton seconds for our units, but again, it's just your call as to which units you prefer to use. In part C, we would like to determine the magnitude of the average force between the bat and the ball. So we would like to find the average force that the bat exerts on the ball. And let's consider a free body diagram before moving forward. So here's our ball, and of course the bat is exerting a force that's directed towards the right, and the Earth is also pulling at the ball with a force, of course, that's known as its weight, so we've included the weight, and the ball will be accelerating primarily towards the right. So we'll indicate that with a rightward acceleration. Now, it's important to note that the bat will exert a force that is much, much, much higher than the weight of the ball. It's so much higher than the weight of the ball that the weight has virtually no influence whatsoever as to what happens to the ball while it's in contact with the bat. And because of that, we can consider the weight to be negligible. And that's generally the case when objects collide. The forces between them are so great that the weight of each object is not generally considered in the calculations of impulse and momentum. So how do we find the force that the bat exerts on the ball? Well, we can rely on the impulse equation once again. Let's take a look at that equation. Here are the two impulse equations. Last time we used mass times final velocity minus mass times initial velocity. In this case, since we're searching for the force, we could use this equation for impulse. Now let's take note that we did just calculate the value for the impulse, and the amount of time was given within the problem, right? Here it is. The amount of time that the bat is in contact with the ball equals 1.5 milliseconds. And so we have everything we need to calculate force. Let's apply this equation. So, impulse just equals, in this case, force, average force, times the change in time. The impulse was derived as 14.5. We're looking for the average force, and the contact time is 1.5 milliseconds. Of course, milli signifies a multiplier of 10 to the minus 3. So the time is actually entered as 1.5 times 10 to the minus 3. And again, let's not forget that milliseconds introduces a 10 to the minus 3 multiplier for the time. Now, if we solve for the average force, we obtain 9,667 newtons, which is much, much larger than the weight of the ball. If we were to calculate the weight of the ball, it's only 145 grams. That weight would be far, far less than the 9,667 newtons that the bat applies to the ball, and therefore the weight is negligible. Let's take a look at Part D. In Part D, we would like to determine the ball's average acceleration while in contact with the bat. And in order to do that, we can apply Newton's second law to the free body diagram that we have drawn earlier. Here's the free body diagram. Of course, this arrow represents the acceleration, and the only force directed in the direction of acceleration is the force of the bat. So let's apply Newton's second law now. It tells us that if we add the forces in the x direction, we either obtain 0 or ma or minus ma. Of course, the free body diagram clearly indicates that we should choose ma, positive ma, because the acceleration is directed towards the right. So ma is our choice, and there's only one force that extends from the summation, and that is the force of the bat. So the force of the bat, and this is the average force that we're referring to, just equals the mass times the acceleration. The mass of the ball, again, is 0.145 kilograms times the acceleration. The force of the bat was just calculated as 9,667 newtons. Let's roll that into our equation. So we have 9,667 equaling 0.145 times the acceleration. If we divide both sides by 0.145, the acceleration equals a very, very large value, 6.667 times 10 to the fourth meters per second squared. That's 66,000 meters per second squared. This acceleration is so high that if we were to view a time-lapsed video of a baseball being struck by a bat, we would notice that the ball flattens. About one half of the ball becomes flat as it contacts the bat under these circumstances. So this is a very, very high acceleration that results from a very, very high force between the bat and the ball. In the last part of the problem, we want to determine the work done by the bat on the ball. Now, we could try to use the definition of work, and let's see what happens. So the work done by the bat would equal the force of the bat times the displacement times the cosine of the angle between the force and the displacement. The only problem with using this equation is we would need to determine the displacement over which the bat and ball were in contact with one another. And I guess we could do that, but I'd like to avoid that. And so in order to avoid having to find the displacement, we could use the work energy theorem. As you recall, the work energy theorem states that W net equals 1/2 mv final squared minus 1/2 m v initial squared. Now in this case, which forces are doing work on the ball? Let's take a look. Once again, here's our free body diagram. Obviously, the bat is doing work on the ball, and the weight is doing work on the ball as well. But again, because the weight is so low in value compared to the force of the bat, we consider the effect of the weight to be negligible. So for all intents and purposes, let's just consider a ball with the force of the bat acting on it, and we can disregard the weight. And therefore, the only object that's doing work on the ball is the bat. And so W net just equals the work done by the bat. And that equals 1/2 mv final squared minus 1/2 mv initial squared. And since we have the initial and final velocities, we can calculate the work done by the bat very quickly. And so let's enter the values. The mass is 0.145. The final velocity of the ball is 60 meters per second directed towards the right, so I'll enter it as a positive value. Minus 1/2, again the mass is 0.145, and the initial velocity of the ball was 40 meters per second traveling towards the left. I'll enter it as a negative. Let's note, by the way, that we don't have to enter it as a negative because when we square it, squaring the negative 40 will produce a positive result. But I'm entering it just for the sake of consistency. And I also want to note that when we enter this value into a calculator, we have to encapsulate it in parentheses, otherwise the calculator won't square the negative in front and we will end up with the wrong result. So make sure you encapsulate the negative 40 before you square it, or you can disregard the negative and just square the 40 as a positive value. So if all's going well, your calculator should be indicating 145 joules for the work done by the bat. And that completes this lecture.